Okay, so what did we talk about last time? It's working. Sweet. So last time we did sort of the LQR problem 3 different ways, right? So we kind of did LQR via shooting using kind of the Pontryagin stuff. Then we kind of wrote down LQR as a QP and solved it like a QP by like solving a KKT system, right? And saw that it has a nice closed form solution in terms of solving a linear system. And then we sort of zoomed in on that linear system and looked at it kind of blockwise and played this back substitution trick where we kind of walked up the blocks of the matrix and derived this thing called the Ricotti equation, right? And that was kind of cool. And in particular, what's like a big deal about that Ricotti thing is that not only does it give you the solution to the QP in kind of a computationally cheaper way than directly inverting, because it exploits the sparsity in those blocks, it also results in a feedback policy that you can then use from any initial condition, and you can use it to stabilize the system with noise and model mismatch and all that kind of good stuff, which is kind of deep and crazy that just like popped out of that. So what we're going to do today is 2 things. The first thing we're going to do is, oh, we also talked about infinite horizon LQR last time, right? I forgot about that. And kind of the idea that those, both the K's, the gains, and those P matrices that we saw, they end up converging to a steady state after you run the backward recursion for a while. And that in a lot of cases in practice, if you have an LTI system, you pretty much just use the infinite horizon solution and just have a single matrix and don't worry about the time varying tail. Okay, so questions about any of that stuff before we move on with today's fun.
Just use the steady state gain. The fluctuation in the cost. This essentially settle, like will there be like a slight suboptimal?
Yeah, I mean, at the end of the day, what's going on there is this idea that like if you only have a little bit of time left before you have to stop, that changes your behavior. So like if I only give you a few time steps, a few moves, then your decisions are actually time dependent. Like you're going to act differently if you only have a few moves to like get to the goal or something like this. Whereas if you have all the time in the universe, you know, you're going to do things, you're going to act differently, right? And so that's kind of like at the heart of this. You'll get, if you have lots of time, basically, then your decisions are not time dependent and it doesn't matter and you get this constant steady state gain. If you only have a little bit of time, then you act differently. And that's what that's kind of really getting at. So if you're solving a short horizon problem and you actually have only a few moves, the infinite horizon solution is kind of wrong and suboptimal. But that's usually not the case, or we usually don't care about that sort of thing in these kind of stabilization problems, right? So I don't know, depends on the scenario. There are scenarios where you legitimately only have a few moves and you're trying to like get to a goal quickly or whatever, in which case you want to use the sort of, you know, time varying sort of stuff. But if you're just trying to like stabilize an inverted pendulum or something, and it's like a steady state thing where you're trying to do disturbance rejection and counteract noise or whatever, and you're going to run it for a while, then infinite horizon is kind of fine. Okay, anybody else? Okay, so let's dig in. So today we're going to do kind of 2 things. The first one is talk about one last little nugget from the LQR problem that you should know about. And that's this idea of controllability. Has anyone seen this before? A couple people. So this is like a classic topic when you look at like theory of linear systems. If anyone's taken like a linear systems theory course, this is like one of the classic things to talk about. So it's just one last little thing. And then we're going to switch gears and we're going to talk about dynamic programming. And that's going to give us kind of another lens on this whole topic. And it's also going to give us another way to think about LQR and kind of everything. It has deep connections to reinforcement learning and all this other stuff. So it's a really deep topic that you should know about. So we're going to kind of start digging into that today. Okay. Before we get rolling, any other questions? Okay, here we go. So first topic, to sort of, in some sense, complete our LQR discussion. So we talked a little bit about things that need to be there for like the problem definition to like have a feasible LQR problem, right? Anyone want to tell me what we, what one of those things are so far from we talked about? Yeah. So we need these like definiteness things on the cost function, right? To like basically have a problem that doesn't blow up to infinity or whatever, right? Okay, so that's cool. It turns out there's some other stuff that you need as well. Properties of the system dynamics, right? So kind of like stupidly, if I have a B matrix that's all zeros or something, and my control like doesn't do anything, then I can't control the system. And there's an infeasibility there that's coming from the dynamics rather than the cost function, right? So that's kind of obvious. It turns out it's a little more subtle. But yeah, essentially you need also some properties of the dynamics, i.e. the actuators have to enter in ways that are sort of general enough that you can tweak all the states over time. Like that's the intuition here, but behind this idea of controllability is that the dynamics have to have enough control inputs and the dynamics have to be sort of coupled across the states in such a way that you have access, maybe not instantaneously, but over time, you can affect all the states. Does that make sense to everybody? So it's a little bit more so. There's this other concept you might have heard of in robotics called under actuation or being fully actuated. And that means that you have a number of inputs that's like equal to your numbers of degrees of freedom. It's like a robot arm, right? I have motors on all my joints and I can instantaneously apply torques on all my degrees of freedom. That's a distinct concept. You can be under actuated and still controllable. And the concept of the key difference between these things is time. If you're fully actuated, it means at any instant in time, you can affect all your states. You can be under actuated, i.e. not able to do that, but still controllable, which means that maybe not instantaneously, but over several time steps, you can affect all your states. So this is a subtle concept that's not just about how many actuators you have. It basically is a property of both the number of actuators, how they enter into the dynamics, and then the other part of the dynamics, in our case, if it's a linear system, the A matrix as well, and kind of how the A matrix couples the states over time. So if there's enough coupling in the A matrix, you can be very under actuated, but over enough time steps, still have the ability to affect all your states. Does that make sense, everybody? Okay, so that was a lot of talking. Let's do the math. So the big question is here, right? Like, how do we know if LQR will work?
So this is only pertaining only with respect to the system. So let's say with respect to the system dynamics, you can technically take the state of the system to any state that you want.
That's another way of thinking about it. It turns out for linear systems, because superposition holds, this is equivalent to this idea of always being able to drive the system to the origin, right? Because it's linear superposition, I can like zero out I can just subtract a constant and make anything the origin. So all I have to worry about is the origin. So yeah, it's basically saying from any arbitrary initial condition, given the control inputs that I have available to me, can I drive the system to the origin? That's a way of thinking about it.
Let's say the environment doesn't allow it, then how do we?
What do you mean by environment?
So let's say my robot is fully controllable. That is, if there's no other constraints.
Yeah.
But if I have an infinitely strong wall around it.
Yeah, so that's a different thing. There's different ways to model that. And so I think in like RL, this concept of like environment is a little bit overloaded and tends to kind of get conflated with dynamics and sort of your, I don't know, your map or your constraints in a funny way. Right now, we're just talking about the dynamics. These ideas, though, of like, what if there's constraints in the environment? There's, in general, these are really hard to get at. For simple constraints, there is some stuff you can do. In particular, we're going to get into convex MPC. If the constraints are convex, and in particular, if they're like polytopic, you can say some things about this. But in general, it's super hard. And like for general non-convex situations, which is honestly everything we really care about, like obstacles are usually non-convex, right? So in that setting, it's actually quite hard to say general things. So yeah, sorry to disappoint you. But for right now, we're just talking about the dynamics. Okay, so we already know this stuff. And basically, what we're going to talk about right now is a special case result specifically for LTI systems. So we're talking about time invariant, linear time invariant systems. There's a nice clean result in that case. In the general time varying case, you can still do it, but it ends up basically being you just try solving the QP. And if the QP is feasible, then it's controllable. And if the QP is infeasible, you're out of luck. So that's kind of, yeah, basically in this case, there's a clean, nice result. In the more general setting, the answer is not very clean, and you just try solving the QP in practice. Okay, so for the time invariant, there's a nice simple answer. Okay, so here we go. This is going to be like a kind of a funny massaging of the LQR problem. So what we're going to think about right now is this thing that actually shows up quite a lot that's closely related to single shooting. It's also called condensing in some contexts. It's called, basically we're going to we're going to take our LQR problem and like turn it into a single shooting problem. And I'll show you that, what I really mean by that. So for a given initial condition, for a given x naught, I can calculate xn by like essentially rolling out the dynamics. And I can, in particular, what we're going to do right now is eliminate the intermediate states. I'm going to like iterate the dynamics a whole bunch and write this such that it's just a function of the u's and the x naught, x and x naught. So in particular, right, if I write xn and I go backwards one step, I've got this, right, xn, axn minus 1 plus bun minus 1. If I want to go back one more time step, I can write this as a times, I plug in the dynamics for xn minus 1. So that's a xn minus 2 plus bun minus 2. And then I've still got my bun minus 1. So what I've done here is I've eliminated xn minus 1, right? And I can keep playing that game and I can go back as far as I want until I just have x naught and then all the u's. Does that make sense? So yeah, this is me basically doing single shooting, if you like. I'm eliminating all the states and just solving for the u's. It's also, you'll see this sometimes called condensing, specifically in the numerical optimization setting where you're like eliminating all the intermediate states. So this is like, I can do this analytically. It turns out this is a really, really bad thing to do numerically. Anyone want to guess why? Yeah. It's very ill conditioned. Yeah, so the sparsity thing's maybe a big deal, maybe not, depending on the problem. But it gets really ill conditioned. And this should be clear. So if I keep carrying this recursion back that we just wrote down, I'm going to get the following thing. I'll get a to the n times x naught plus a to the n minus 1 bu naught plus a to the n minus 2 bu1 plus dot, dot, dot out to bun minus 1. So I'm going to get like, you know, a raised to a whole bunch of powers, right? So I'm like propagating these things through. And yeah, the ill conditioning thing comes in. So if my system, say my system's controllable, right? All good. I can always do what I want to it. But let's say it's open loop unstable. What I mean by open loop unstable is like, think about an inverted pendulum. Perfectly sort of stabilizable if I have, you know, control here, but the A matrix is unstable. So in discrete time, what does an unstable A matrix mean? Outside the unit circle, bigger than 1. So let's say I do this over like 1,000 time steps. What is a to the n going to do? The n's 1,000. So if a has norm bigger than 1, a to the n is going to blow up. So this is what we mean by ill conditioning. Like I can't do this over a long horizon if the system is open loop unstable. If the A matrix is unstable, A to the n is going to blow up to infinity for large n. So this becomes just horrendous, and you never, ever want to do this in real life. Cool. So there's a magic trick that's going to mean we don't actually have to do this for what we're going to talk about right now. But in general, you should never do this. This is why multiple shooting, single shooting is a bad idea. In the linear case, it's really obvious that it's a bad idea because if the system's unstable, A to the n blows up on you. In the nonlinear case, the same thing happens. Right. So this is why, you know, the vanishing exploding gradient phenomena in RL, the tail wagging the dog thing we talked about here when we talked Pontryagin. This is kind of at the heart of why it's a bad idea. Okay, cool. So this, and then what I'm going to do next is I'm going to package that result into a matrix. So I'm going to write it like so. So we've got B, then A times B, then A squared B, dot, 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 all the way to A to the n minus 1 B. And I'm going to stack the controls over here. So I've got U n minus 1, U n minus 2, U n minus 3, dot, 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 all the way to U naught in a vector. And then, so I stack all the controls, and then I'm going to add on the first state, right? So I've got a to the n x naught over here. Make sense? So I rewrote that thing that we had up there just in the form of like a big matrix times all the u's stacked together, and then the x naught term. Cool? Okay, so now remember what we're trying to do. We're trying to drive the system to the origin from any x naught, right? So if I have this thing I just wrote down, I have like say n minus 1 time steps worth of u's, and I want this thing to always go to the origin. This is a linear system that in principle I could solve for those u's. But what does that matrix look like? And we're going to give this matrix a name. We're going to call this big matrix capital C. What kind of matrix is C? Is it, well, I mean, just what size is it? Is this a square matrix? No, it's not square. So it's not like on the face of it invertible. It's a short fat matrix, right? So this is in some sense like basically the message here is this. Have you ever seen what kind of problems have short fat matrices? Yeah, it's sort of underdetermined, right? And it's we're gonna solve this like a least squares problem. Cool. So I guess the way of saying this is this whole thing is, oops. This is equivalent to a least squares problem for the u's. So for u naught to n minus 1, right? So we're basically trying to set xn equal to 0. And then if we do that, so I guess I should say without loss of generality, we solve for xn is the origin, and we just kind of put this all together. So now if I kind of like slightly rearrange that equation, I'm going to solve for the u's. So I've got like un minus 1, un minus 2, dot, 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 u naught equals. So I'm going to like write a little thing down and we'll talk about it. You've probably seen this before. So I can play this trick called a pseudo-inverse, where I take C and I multiply both sides by like C transpose and then like do some massaging, right? And that looks like this: C transpose, C transpose inverse, and then the stuff we had back there. I could write it this way, right? If in general. Cool. So I guess I don't have to, make x naught 0, but it's fine if you do. It doesn't matter. Cool. So now we have this least squares problem. So given an any x naught, and I guess any xn if you want to, right? I can solve this least squares problem for all the u's. Make sense? And this thing here is called a pseudo-inverse. Or also known as a Moore-Penrose pseudo-inverse. These are like the classic how to solve a least squares problem kind of thing, right? Sometimes in least squares, you hear this called the normal equations. Anyone heard that before? Okay, so no one's heard of normal equations from least squares? I should definitely know about that. Okay, so so this is a fine thing to write down, and in theory, it's fine. In practice, you should never do this, just as a fun fact. Does anyone know about this? how do you actually solve least squares problems for real?
SVD.
You could do SVD, that's more expensive than you need. The right thing to do here is a QR factorization in general for least squares problems. The reason you don't do it is back to the ill conditioning thing. If I take C transpose, I'm squaring C, and the condition number of that is then double what it would have been otherwise. And higher condition numbers are bad when solving linear systems. So I'm like squaring this thing, then inverting it. That's all bad. If I do a QR factorization instead, I can avoid the squaring, blah, blah, blah. Fun facts, you can look it up on Wikipedia. You should check out pseudo-inverses. They show up a lot. It's a useful thing to know about. Okay, so now that I have this thing, what has to be true for this problem to have a solution? Like, what conditions do I need on that pseudo-inversey thing, the C, for this to work out? I need C transpose to be full rank, to be invertible, right? Cool. So that's, okay, so that's kind of the heart of it. So for that to be true, I can actually get a condition just on the C matrix alone, which is really simple. It's that rank of C has to equal little n, where n is the state dimension of the problem. Does that make sense to everybody? So if C has rank n, then this CC transpose thing will have rank n. It's an n by n matrix. Life is good. I can invert it now. And then this thing has a solution. Okay, so that seems cool. That's fine. And in principle, by the way, I can do what I just did here for any problem, right? I could do this for a linear time varying problem, and that would be okay. Because I can I can do this thing, right, with all the A's and B's for time varying A and B, right? That works out for A sub K's and B sub K's just fine. So up to here, I can do this for LTV, and that's okay. But it doesn't really save you anything over just solving the QP. Also, fun fact, if anyone in here heard of a Gramian from like a linear systems class? Do you recognize this? I won't blame you if you don't, because they don't teach it this way in those linear systems classes, I think much to their detriment. That CC transpose thing in there is the Gramian from linear systems theory. It's the controllability Gramian. So you know how they tell you, oh, you have to use this Gramian thing if it's LTV? Literally that Gramian thing is CC transpose. They don't teach it that way because they do it in continuous time and it's a weird integral thing, but in discrete time, it turns into a sum and it's equivalent to CC transpose in there. Fun facts if anyone hasn't, but yeah, if you haven't seen that before, don't worry about it. So this is general, works for LTV or LTI, but now in the LTI case, something special happens. It turns out for LTI's problems, I can stop inside this control. So this thing, this big C is C for controllability. It's called the controllability matrix. It turns out if your problem is LTI, you can stop at little n time steps. So right for here, I might have some long horizon on my problem. I want to check if it's controllable. Turns out if the system is LTI, I only have to carry this C matrix out for n time steps. Can anyone tell me why? Not quite. You got it. Yeah. Okay. So this is a big deal. This is so all this stuff is pretty simple. This is like the one move that requires a little bit fancier linear algebra knowledge. So there's this thing called the Cayley-Hamilton theorem. Who's heard of that? Decent number of you guys from like a linear algebra class. Can anyone tell me what the Cayley-Hamilton theorem says? Yeah, that's a terrible way to say it, I think, personally. That doesn't really tell you anything useful.
You derive from there.
What's the useful result? That's why I can make this move. That's also true, but it's not why I can do this. There's another statement of that that's like, I think the useful version of it that actually is the deeper one. Yeah. Yes, that is what you want. And what that says, another version of that is that for any matrix, I can write any power of it in terms of a linear combination of the powers 1 through n. So I can write the like 100,000th millionth power, like I can write a to the 10,032 in terms of just a 1 through n for an n by n matrix. So it says any matrix of like, n by n matrix, any power of it can be written in terms of just a linear combination of a 1 through n, which is like, that's the real result. That's like all those other things follow from there. And that's why you can stop here. Okay. So we'll write that down. Kelm-Hamilton theorem says that a to the big N can be written in terms of a linear combination of lower powers of n, lower powers of a up to little n, where little n is the dimension of the state and also the dimensions of a, right? It's n by n. Cool. So specifically, it says the following in math, right? It says a to the n for any arbitrary n can be written as a sum from k equals 0 to n minus 1 alpha sub n. I guess we're going to do k's here. Alpha k a to the k for some alpha weights, right? For some linear weights. Cool. Okay, so therefore, if that's true, then in this controllability matrix, adding sort of more time steps than little n does nothing for me, right? It's not going to change the rank in particular, right? Because if this linear combination thing is true, then having higher powers of n doesn't change the rank, right? Because it's linear combination, so it's sort of linearly dependent, doesn't change, right, the rank of the matrix. Okay, so therefore, adding more sort of time steps or equivalently columns to C can't increase the rank. And we have then that this controllability matrix, we're going to define it now as just having sort of looking like the following, right? So B, A, B, dot, 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 up to A to the n, little n minus 1 times B, right? So it's got little n time steps worth of U's basically in it. And this thing is called the controllability matrix. So now we have this kind of nice general theory for LQR where we know, all these nice things about it. In particular, if I give you a linear system or you take some other, you linearize some nonlinear system, whatever, if you want to develop a controller for it, write down some Q's and R's that have some definiteness, considerations, right? Positive, definite, basically. And then you check this thing. If this thing has rank n, system's controllable, all good, good to go. So question now on this thing. If this thing is fully actuated in the sort of, robotic sense, how many time steps do I have to go in here? 1, right? Because I basically have instantaneous control over all the degrees. So I just need the B. So what does under actuation mean then? Or so I said the condition for a system to be fully actuated is basically that the B in the manipulator equation is full rank, so that this thing is true for only a single time step. That means here though, yeah, you basically what this is saying is if the dynamics are kind of rich enough in some sense, even if B is very rank deficient, by hitting it with A a bunch of times like this, I'm like basically, if the degrees of freedom are coupled over time through the A, then over enough time steps, I can still access the full state vector. That's kind of what it's saying. There's a related concept, by the way, called controllability index of a system, which is how many time steps it takes to sort of hit the whole state to be controllable fully. So, okay. Any questions about this stuff? Okay, cool. So if you have taken, yeah, please.
for CC transpose to be equal to 1, why does it have to be the dimension of
So the C thing, if I take CC transpose, how big is that?
CC transpose is very particular. Should be use dimension of U multiplied.
Oh, what's it? Just look at the right-hand side there. What's it multiplying? Yep.
CC transpose, right? This is the pseudo.
Yeah, but CC transpose, just CC transpose, the thing that you have to invert, that's a square matrix, and it's n by n. So for that inverse to be possible, yes, absolutely.
So these.
Yeah, I mean, you work it out if you don't believe me. Yeah, the way to think about it is the B is it's only U wide, but it's size X tall, right? So the C matrix is little n tall, right? So that's what ends up mattering when you do the CC transpose. Cool. Okay, so I think we're kind of done with LQR stuff, at least for now. This is again, I like want to emphasize how useful this is. This is like you can solve with LQR and like some minor extensions, many of which we're going to get into later in the class. You can solve almost every problem in control. It's like kind of nuts. So you can do like this stuff is easy. You can do trajectory tracking with time varying LQR, i.e. the LTV version where you linearize along a trajectory. You can actually solve nonlinear trajectory optimization problems using what's called iterative LQR, which is where you like basically treat LQR as like Newton method, and you like relinearize and resolve LQR to update until you converge. There's like multi-agent game theory versions of this stuff that are called linear quadratic games. There's robust versions of it. Like almost every problem in control theory, if you like, look at the simplest version of it, ends up being some flavor of LQR problem. So it shows up absolutely everywhere. It's super, super useful. And like, if you kind of become really familiar with this, it's like one of the most useful things ever. It's been called famously like the crown jewel of control theory. It's probably the most useful thing you'll ever learn in control. So, you should take it seriously and maybe, circle back on it. Okay, with that, yeah.
Like in most of the cost functions, you always take some mathematical norm.
Because I mean, the cost function is arbitrary. You get to make it up. So if as long as a quadratic cost will work for you, as long as you don't have other reasons to choose something different, you might as well, right? Like we get to make that part up. And then if you linearize the dynamics, which you can always do locally, you end up with an LQR problem. So yeah, I don't know. As long as the dynamics and costs are smooth, if you Taylor expand, you end up with this as like the lowest order problem that's worth looking at, right? It shows up a lot. Okay, cool. So with that, we're gonna now sort of switch gears, kind of in a big way, but we'll still see lots of LQR randomly throughout the semester in different guises. So now we're going to talk about is dynamic programming. Who's seen this before? Bunch of you. Cool. Where have you seen this before? Robot learning. Cool. Yeah. So, I mean, this is obviously it's foundational to like all of kind of, RL stuff as well. It's all the same stuff. So we're going to try to look at it from like a very, very basic kind of perspective and try to get you some intuition for what's actually going on here. And we're going to start out with this thing called Bellman's principle. Okay, so the idea here, this is also called the principle of optimality, which, whatever. So the idea here is that like we've already seen how optimal control problems have a lot of structure, right? In particular, we saw, the block structure in the QP for LQR, and like you could do this fancy walk down the blocks thing and get this Riccati thing. So there's a lot of structure in there. And in particular, the structure that matters here is this kind of temporal structure. So we would say they have like an inherently sequential structure. So we kind of all have some intuition for what this means. Like one way of saying it is that there's kind of this arrow of time flavor here where past control inputs can only affect future states, and that like future control moves can't affect the past, right? That's kind of there's this kind of arrow of time causality thing happening, right? And that's deep. That actually like is kind of where that block structure is coming from in the problems, right? So let's write that down. Past control inputs can only affect future states. Future inputs can't affect past states. Okay, so basically that intuitive thing we just said is really what Bellman's principle is. And it's just stating it like in a bit more kind of like mathematical language. So Bellman's principle, also known as the principle of optimality, sort of formalizes this. Okay, and like kind of says what this means for optimal trajectories of a control problem. So if I imagine I have some trajectory, and I'm going to draw like a very bad cartoon trajectory here. So like this is time, let's say, and this is like the state for something really dumb. And let's say we start out over here at x naught, and we kind of like wiggle around a bunch. And then we get to some goal over here, xn. Let's say that trajectory is optimal for whatever problem I had. Let's imagine for a second that I like randomly stopped in the middle here somewhere. And I now solved like at some xk. And let's say I gave you a new optimal control problem that started at that xk. And you didn't know anything about the past. You just knew that that was your initial condition. You had that much time to get to that xn. What's the solution to that new subproblem starting from xk? The same trajectory, right? And the logic is that if I took that subproblem starting from xk, if that had a lower cost solution, say going like this way, if that were lower cost on this new subproblem, then I would have taken it on the original longer problem because it's lower cost. Cool. So that's sort of obvious. Like all of this is actually very, very obvious and like very intuitive. So if this path at lower cost, starting at xk, I would have taken it starting from x naught. And sort of saying that the other way around, like this, this can't be like the only optimal thing for this sub trajectory has to be the one from the longer trajectory, right? So like another way of saying this is that sub trajectories, and when I say sub trajectory, I mean specifically this, right? If I start at some intermediate point on the optimal trajectory and solve a shorter horizon optimal control problem with the same everything else, but just starting somewhere in the middle, that sub trajectory of the original optimal trajectory has to be that solution to that smaller problem, because this obvious fact is true, right? All right. Have to be optimal for, we'll say, the appropriately defined subproblem. Okay. Cool. So that's kind of it. Anyone have any questions about that? Yeah. So if I start there and I just like shrink the horizon on the problem, right? And I keep everything the same, the cost and constraints same on the original problem. I just make it a shorter problem with the starting initial condition being some state in the middle of the original trajectory. That has to be true. This has to be true given that. It doesn't have to be fixed. If I ended up there because of the minimizing the cost function, if I keep the same cost, it doesn't have to be a terminal constraint necessarily that says you have to end at xn. It's saying that if I shrink the problem and start with initial conditions somewhere along that original trajectory and everything else is the same, I will get the same answer.
Shrinking it from the start, or if you shrink it from.
If you shrink it for the back, yeah, this can be subtle. Like in particular, if I had some terminal cost that was different from the stage cost or whatever, then it could be, yeah, different. So yeah, this is a good point. It's specifically shrinking it from the head and not the tail. Yeah, yeah.
So does this only apply to time invariant systems then?
No, it's a general statement. Yeah. So if I sort of like shrink the problem from the head, leave everything the same. So it could be time varying, could be whatever. This fact holds. Cool. Okay. So this has, it turns out, some like very deep consequences and lets us kind of derive this dynamic programming idea. And essentially, what dynamic programming says, or what this like Bellman principle kind of telling us, is that, and yeah, you made a really good point that this only applies shrinking from the head. It does not hold if I shrink from the tail, because you could have terminal costs, blah, blah, blah. So specifically because of that, right, what this really tells us is that if I have a problem like this, maybe I want to think about starting from the end and working backwards. That's kind of what this is getting at, right? So let's write that down. Bellman's principle sort of suggests starting from the end of the trajectory and working backwards. Does that sound familiar? So that should sound very familiar at this point, right? Because we've already seen like Pontryagin with the lambdas going backwards, the costates going backwards, and then Ricotti runs backwards in time, right? So these are all very closely connected ideas. And all of it at the end is coming from this basic intuitive, structural property of these problems. So we've already seen this a couple times. With Ricotti and Pontryagin. Okay, so here's how we're going to sort of now mathematically formalize this thing. So we're going to now define this, this new function, which if you've seen this before, then you've seen this before. We're going to call it, but it does go by different names in the learning community versus control community. So we're going to call this thing the optimal cost to go, or just cost to go for short. In machine learning, like RL, what do they call this thing? The value function. Yeah. Who's heard of value function? Who's heard of cost to go? Yeah, fewer people. So it's the same thing. So we'll write that down. I personally think that cost to go makes more sense and actually means something, whereas value function doesn't seem to have any actual meaning to me. It seems very vague and whatever, but whatever. You can take your pick. Doesn't matter, either one. So we're going to call this thing V. And if we index it as a function of time, it's going to be in discrete time V sub k of x. So in particular, this is a function of just the state.
So here the optimal one is the not any.
Yeah, so let me define this thing. Yeah, maybe that'll clear things up. So what we mean by this is this function tells me the cost that will be incurred starting from some state x, and in general also it can be time varying problem, so some time step k. It tells me the cost I will incur starting from time k at some given state x if I act optimally from there on out to the end of the problem. Make sense? That's what this encodes. So yeah, it is assuming that I'm acting optimally, i.e. that I rolled it out with the optimal policy is another way of saying that, right?
Because like the learning community.
You often do this with suboptimal rollouts, right? Yeah, so in particular, when I say optimal cost to go, that's what I mean. And in here, we're basically always going to do it in the context of it being optimal. Yeah, so we're always going to think about it as optimal cost to go. And because of that in here, it won't be ambiguous. And when I say value function or cost to go function, I always mean the optimal one. So this encodes the cost incurred starting from state X at time K if we act optimally. Like from there on out, right? And this is actually super deep. Like if you've seen this before, you kind of know, right, that if I know this V of X function, if I can figure out a way to compute this, to learn it, whatever, if I really have the true V, I've basically solved the whole problem. And I know everything there is to know about the problem from that value function thing, cost to go function. Okay, yeah.
Do these typically have like a time horizon? Like in our case, like we ended our argument create like xn because of like some
Can be both. So yeah, that comes from the problem, right? So I can write down a finite horizon problem, or I can write down an infinite horizon problem. So for a given problem, I get one of these V's, right? And it depends on the problem. It can be, so I wrote it V sub k here. This is obviously a finite time one, right? Then if it's an infinite time one, then it converges to a steady state V that doesn't have any time index on it, right? And then it's just V of X for any, it's not time dependent, right? Make sense? Okay, so yeah, this is problem dependent. Depends on the exact problem you wrote down, but yeah, all the usual things apply. And the deep thing here is, which we'll get into a little bit, if I figure this thing out somehow, then I'm done. This is it. Like that's all there is to know. You've solved the whole problem. Okay, so now what we're gonna do is do this for an LQR problem, because it's the kind we know how to solve and the math works out nicely. But you should know that this works in general, right? This is a very general idea, and it's also the backing of like most modern RL and stuff, which we'll talk about a little more once we've sort of done it. But I really think like there's a ton of insight here doing it for like LQR. That's okay. So we're gonna do LQR. And remember for LQR, we defined the cost function in such a way we had this terminal cost, right? We had a Qn. So for the LQR problem, the cost to go at time step n, and this is getting back to the whole principle of optimality, why you start at the end and work backwards. Well, if I have no control moves left and I'm at state X at time n, the optimal cost to go is just the terminal cost. I can't do anything else. So that's what I'm left with. So there you go. So this is just 1/2 X transpose QNX. Cool. And in a bit of foreshadowing, I'm going to write this as 1/2 X transpose ENX. And it turns out that, well, maybe we'll just do this. So that's what it is here at time n. And now what we're going to do is we're going to do, it's called a Bellman recursion. We're going to go backwards in time one step. And then we're going to kind of see what it looks like as I back up in time from the last time step. And intuitively, the idea here is like, this is what dynamic programming is all about. It says start at the end, work backwards. And what you can basically end up doing is solving tiny one-time step problems recursively backwards in time instead of solving one giant problem for the whole thing at once, right? So let's do that. So we're going to back up one step. And we're going to try to calculate this Vn minus 1 of X, right? So we got Vn of X, that was easy. Now we're going to get Vn minus 1. So in particular, what we're going to do is I'll write down the definition of it, and then we'll try to like simplify it down a bit. So what we're going to do is basically, remember, this is saying if I act optimally from that time step to the goal. So I'm going to write down that optimization problem. And it's just like a one-step LQR problem. So I only have one U to optimize over. And I'm minimizing one time step worth of the cost function. So that's going to look like xn minus 1 transpose q xn minus 1. And that could be a qn minus 1, right? If I'm time varying, whatever. You can figure that out. I'm going to avoid writing subscripts to save myself a little bit here. And then this u that I'm trying to solve for. And then I've got the terminal cost, which is just that x transpose qn of x. In this context, I'm going to write it in a suggestive way as Vn of, and I'm going to plug the dynamics in. So A times xn minus 1 plus B times un minus 1, right? Which is equivalent, right? Makes sense? And I'm writing it this way on purpose because it's going to set us up for some recursive stuff in a sec. Okay, so And yeah, and in general, right, could be a sub whatever. You can have subscripts. I'm just gonna make life a little easier. Now what we're gonna do is I'm gonna like make a little break in here, and we're gonna solve that minimization problem in closed form. And then we're gonna keep trucking, but I'll like kind of put a little break in here. So let's do that. So if I kind of expand this out, in particular, I wrote it like Vn of whatever. I'm going to now plug that all in and write it out in its kind of full messiness. So one thing to note is that the first term on here, which is that xn minus 1 term, if I minimize over u, that drops out and doesn't matter, right? Okay, so we're going to leave that off, and then I'm going to just get this term. And then I'm going to expand out the second term. So it's really just x transpose q and x. I'm going to write it with the dynamics plugged in for that xn. So un minus 1, and then this transpose, and I'm going to still write it as pn for reasons that'll become clear in a sec. And then, just this on the other side. Everyone see how I did that? I just plugged in the dynamics into this guy here. Okay.
You still need the 1/2? Or is
Yeah, you're right. You're right. Thanks. Good catch. Yeah.
UTRU?
Yes. You're totally right. It turns out if it doesn't actually matter,
All of them go away.
it does. It's basically a 2 that divides out because I set it equal to 0. But yeah, for consistency, I should write it that way. You're right. Good catch. Okay. Yeah.
So is the U and the UR U also gonna be n minus 1?
It will be, but I'm doing it on purpose like this because the real un minus 1 is the one that is like the argument of this problem. See what I'm saying? So I'm minimizing over u. The minimizer of that is the un minus 1. But right now, yeah, I mean, this is a stupid detail. It doesn't really matter. But yes, it absolutely is. But if I were being very pedantic about this, I would write un minus 1 equals argmin over u of this thing. Does that make sense?
Getting UN minus 1 is the one plugging into the xn.
Oh, yeah. Thank you again. I'm being like a little bit inconsistent. So they're all the same u's. Xn minus 1 is like sort of given, right? It's like an initial condition-y thing. This u, I'm just being a little bit careful and pedantic about the notation. Specifically, un minus 1 is the particular u that minimizes this thing with respect to u. But yeah, totally good. Okay, so this thing is a nice quadratic function. It's convex because I'm assuming I made nice choices for Q and R as I'm supposed to. Yeah. Because it doesn't matter when I minimize this thing over U. It doesn't affect the solution. I'm only min over U. So that thing just looks like a constant, right? It'll come back in a second, but for this sub problem, it doesn't matter. Okay, so cool. So because this is a nice convex quadratic thing, because of the restrictions on Q and R and all that good stuff, I can solve it. I can just set the gradient equal to 0. If I do that, I'm going to get RU plus B transpose PN A X n minus 1 plus BU equals 0. And to be super clear about it, right, this is me writing down grad of this thing respect to U equals 0. And then, right, from here, I can just rearrange this and solve explicitly for U. So I'll get UN minus 1 equals minus R plus B transpose P N B inverse B Pn A X n minus 1. Boom. Okay, now this should start looking maybe a little bit familiar. And we're going to start making putting some labels on some things. So this thing that multiplies the x, we're going to call Kn minus 1. And this is a feedback policy now that's giving me u as a function of x. Is this starting to look familiar to anyone? Interesting. What's going on? Okay, so I did that.
The fact that we're able to do this for any general xn minus 1 is because the LQR setting.
It's because of this like temporal structure. The fact that I can do it in closed form and that it ends up being a linear policy is a property of LQR, right? But
in the notion that we take a state and we try to optimize from that state. But if you want to do it for any general state,
well, dynamic programming, actually, usually you're doing it for the general any state thing.
all the states, but here we have a closed form for it.
We did it for all the states here. I didn't do this for a particular X. This is for any X.
Yeah, but the optimal, typically the optimal control that we get is based on that state itself. We get a closed form solution. So things are simple.
I did this for the whole thing. I didn't pick any particular X in any of these calculations. And I've got the optimal policy for any X here. I'm solving, so to be clear, I think this is subtle, right? Here, I'm not solving for a particular trajectory, I'm solving for a value function. And I'm also, as part of this, getting a feedback policy. I'm solving for the global value function and the global optimal policy, not a particular trajectory.
What that would look like in your value function if you like plot it is like just like follow a value, right? Of like the minimum.
Yeah.
Yeah.
Yeah. And so this is coming. 1 second. So what we're going to do now is we're going to plug that optimal policy back in and derive. What we did so far is get this policy thing. We didn't actually get the value function yet for Vn minus 1, right? So we're going to do that right now. So we're going to plug in particular, right? We're going to plug u equals minus kx back into the value function thing up above. And I'll like label these with some stars. So we're very clear about this. So back into this guy, right? My equation for Vn minus 1 that I wrote down up here. I was trying to minimize with respect to u. Now I have the optimal thing, the optimal u. So I'll plug the optimal u back in, and that's going to give me the optimal cost to go for value function. So Vn minus 1 of x equals, and again, I literally am just plugging that definition for k into the other thing. That's up there, and it's just a function of x because I optimized over u. I got rid of u, right? I made u a function of x with that feedback policy. So now the v is just a function of x again. So in particular, it looks like this. Okay, that's the whole thing, right? And it's again, it's just that line with u equals minus kx plugged in everywhere. Cool. And I get this thing. And now, what do you think we call the matrix in the bracket? Pn minus 1. And now we have a recursion because we have Vn minus 1 of x equals 1/2 x transpose Pn minus 1 of x. And it looks exactly the same as where we started, where we had Pn. So now we can kind of keep this going backward in time until we get to the beginning or until we converge to steady state if it's infinite horizon or whatever you want. So now we have a backward recursion for k and p that we iterate until k equals 0 or whatever we feel like. And this should obviously look very, very familiar to everyone. We've seen this thing before. What's this thing called? This is called Riccati recursion again. So last time we did it as this like matrix sparsity back substitution thing. This time we got the same answer essentially from dynamic programming. So these are, again, very related things. Dynamic programming, they're the same thing, which is kind of interesting. Again, there's like deep connections between all these ideas and like the real root here of what's going on. Like these are just me putting fancy names on all this stuff. Like what's really happening there is that the problem has that arrow of time temporal structure. And that in one case results in a particular matrix sparsity pattern that is amenable to like doing back substitution. And in another case, we can think about it in this maybe more general case, right? Like as this like dynamic programming, you know, value function calculation, but they're the same. I'm doing this, they're the same thing, right?
is coming due to the causality.
Yes, yeah. The matrix sparsity pattern is a direct result of this temporal arrow of time causality thing, as is the dynamic programming thing. They're both like manifestations of the same underlying, concept. The dynamic programming version is a bit more general, right? This is like general for any nonlinear blah blah blah. The matrix sparsity story was particularly for like the linearized sort of LQR version of the problem because you can write it down as a matrix. But that same structure shows up if I solve a nonlinear trajectory optimization, I do Newton. So that's also like quite general. They're just kind of different sides of the same coin, right? Yeah,
When you say until k equals 0, is that your time step k or is that like your controller k?
that's like time k, whatever, for a finite horizon problem, like till the beginning is what I'm trying to say. Yeah, yeah. Anybody else? So this is kind of cool. So now what I'm going to do is like we just did the LQR version. I'm going to write down now like the general case dynamic programming algorithm, of which Ricotti is special cased to LQR. So Ricotti is a special case of dynamic programming for the LQR problem. Okay, so let's write this down. So we start out at time step n with this Vn, basically getting set equal to our terminal cost. And again, this is fully general now, what I'm about to write down. So we do this and we set k equal to n. And then we run this backwards where we kind of do while k, say, is greater than 1, we're going to compute Vn minus 1 of x as a min over u. And in general, we can put constraints on this, just like we did in the Pontryagin scenario, where this u can be drawn from some set u, i.e. it can have bounds on it, inequalities, whatever. We're going to do this, but this is importantly, this is a one-step min. It's a min over a particular u at a particular time step. And we're going to have the one-step cost in there, right? So for LQR, that's a single x transpose qs, u transpose ru, single time step. And we're going to have the cost to go for the next time step with the dynamics plugged in, so that it's kind of mapping the current state and control forward to the next state, plugging that in. And the idea is if I go backwards, that second term with the cost to go function, with the dynamics plugged in, that includes the optimal cost for the whole rest of the problem, for the whole future. And by computing that again, I can basically back up one step at a time and recursively compute that thing until I get to the beginning of time, as far as I'm concerned. And now I have the cost for the whole problem in there. And that encodes the whole answer. Yeah.
So it's supposed to be v k minus 1.
Sorry, I wrote, so it's vk minus 1 on the left-hand side. Yeah, not n. My bad. Thank you. And I'm going to do this backwards, and I'm going to set k equal to k minus 1 and keep going. And this is kind of the pseudocode for it. So that's the whole thing. And then the kind of message here is, if I can do this, which in the LQR case, we clearly can. So if we know V, like if we can solve this thing for all Ks and all Xs or whatever, then we have everything. In particular, we basically get the optimal policy from this trivially, or almost. I shouldn't say that, actually. There's some more to say about this. The optimal policy is easy to write down. It's then UK of X, the feedback policy, is argmin over U in, whatever my bounds are, of one step cost plus the cost to go with this guy in here. So I can solve this little optimization problem over just a single time step. And the answer to that is the optimal control. Right. Cool. And we did this already. It happens for LQR. I can do that min in closed form and I get u equals minus k. Okay, cool. So any questions about this? This is totally general for any nonlinear problem in principle. I can do this and get the whole thing. Yeah.
You basically end up with in the LQR case, you end up with your P of k minus 1, and you're just accumulating those, and then that you can combine it, you can multiply as many as you want together, like get the.
Yeah, I recursively keep going backwards. I get all the P's and all the K's in the LQR case, right?
Mhm.
So to say something very particularly right, and turns out the reason this works well for LQR is that the optimal policy ends up being linear feedback,
Mhm.
and the optimal cost to go ends up being a quadratic function with a positive definite or positive semi-definite P.
Mhm.
So the key thing there is both of those kinds of functions are easy to write down in terms of matrices. And I can do a bunch of matrix calculations and get the functions. In general, for arbitrary nonlinear problems, those functions can be arbitrarily terrible and hard to write down. And so this doesn't work so well in more general cases. It happens that for LQR, it works extremely well. Okay, so some notes about this that you should know about, and probably many of you do if you've done any kind of, if you've seen this in other contexts. So DP equations, the stuff we just wrote down, can be equivalently written in a slightly different way that you maybe have seen. In terms of this thing called the action value or Q function. We're not going to call it Q because we're using Q and LQR for other things and it's kind of overloaded. We're going to call it S because I don't know. I picked another letter that wasn't taken by something else. I'm trying to avoid overloading notation too much. Who's seen this before? A few, not a ton. Okay, so then we should talk about it a little bit. Okay, so this thing that's called the action value function, or just Q function. The real name is action value function. It's usually written as a big Q, big letter Q in a lot of the literature, so people just call it Q function for short. And it looks like this. So we're gonna use big S, and so we'll write it as S sub K. Yes, when we talk about this, it's always the optimal one. So yeah, to be very, very clear, we're never going to make a not optimal value function or action value function in this class. Cool. I'll say it very, very clear.
The action value, it talks about what kind of action you want to take next week. So it kind of makes sense to
I disagree. I think that's just wrong. And for the following, like value functions, like cost to go functions, they're supposed to be the optimal one. In RL land, people do weirder things for reasons. There's reasons they do it this way. But what they're doing really when you have a suboptimal one, it's always in the context of like you're iterating, trying to get the optimal one, and it's some iterate along the way that's suboptimal because you haven't converged yet, right? So like, I would say that's just an approximate, not yet converged, optimal value function. You're trying, but you haven't gotten there yet, right? So I would probably call that something else. If anything, I would call it a suboptimal value function approximation or something, right? So in here, it's always the optimal one. Okay, so it's the following thing. So literally what it is, it's the thing that's inside here. So I'm basically taking the value function, plugging the dynamics in, and writing and adding on the one-step cost. So it's the entire thing that's inside the argument in the dynamic programming problem, right? So this thing. Note it shows up a lot, right? So cool. The thing inside the min in dynamic programming is what this action value function thing is. So it's L of x u plus vk plus 1 with the dynamics plugged in. That's action value function or Q function. And as an aside, this is usually written as Q of XU. We're not going to write it that way for obvious reasons. So we'll use S, just so you know. So why would I do this? For those of you who are experienced with RL, why would I care about this? Why would I ever do this? It's sort of convenient in that it's what explicitly shows up in these equations anyway. So that's cool. But there's a deeper reason why I would do this.
the Q as a function.
So this actually gets at the heart of like the big differences between RL and optimal control. In optimal control, I mean, there's a lot of gray area and there's a big continuum between like what people typically do in RL and what people do in optimal control. So these are not absolutes, but in general, in optimal control land, we sometimes call it model-based control. We are generally assuming that we have some kind of at least approximate rough dynamics model. So we have an F somehow, however you got it. Could be data-driven, could be a neural network approximator for F, could be anything, but we assume we have access to something there. Whereas in most RL contexts, you do model-free RL where you don't assume access to an F. Cool. So by rewriting all the dynamic programming stuff in terms of this S, and remember when I do, deep RL, I'm directly learning these functions with a function approximator, right? So if I do model-free RL, I can directly use a function approximator to learn S instead of having two function approximators to separately learn V and F. So basically, S is basically the composition of V and S and the cost to go and all of it shoved into one big function. Whereas in optimal control, we break those apart and I have, the one-step cost, the value function, and the dynamics model kind of all separated. This kind of shoves them all together such that I only have to worry about learning one function instead of 2 or 3 separate functions. Does that make sense? So this is like a popular thing to do in the context of model-free RL. You could also, by the way, do model-based RL, where you learn a V and an F separately, and it looks more like this, right? So these are all kind of the same ideas. They're just like mixed around in different combinations. But that's why this would be maybe advantageous in certain contexts to use this thing directly to specifically avoid the need for an explicit F. Okay, any questions about that? So we have some more notes. So now we have to talk about the curse. Who knows about the curse? Yeah, dynamic programming is famously cursed. Bellman himself said so. So, it must be true. Okay, so basically, yeah, he did have computers. They were obviously not as good as ours, but yeah, the curse is real. The curse is there. It doesn't matter how many GPUs you have, right? Kind of fighting a very bad exponential trends are just bad. You can't fight those too hard. Okay, so some notes, right? This dynamic programming thing is remember we talked about KKT conditions being just necessary conditions, but not sufficient, right? And then we talked about second order sufficiency, blah, 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 for a minimizer. So it turns out DP, the stuff we just did, dynamic programming, also, by the way, Pontryagin, because it's basically KKT conditions, Pontryagin are necessary conditions. They're not sufficient for a global optimum. Dynamic programming, however, is a sufficient condition for a global optimum. So if you can do dynamic programming and get an answer, that's it. That's the whole thing. So this is like the gold standard if you can do it. Which is kind of awesome. No, this is more than second order, right? Like in general, this is like the whole nonlinear beast in here. So if I can actually do this recursively and get the solution, that's it. I've solved the entire problem. But this is the problem. This is only tractable for really simple problems in general. So to be particular about it, I can do it for LQR basically for any size problem, because it ends up reducing to the Ricotti equation, right? To basic matrix math, and I can solve really, really big matrix equations with GPUs and stuff. So I can always basically do it for LQR problems, and then for general nonlinear problems, if it's sufficiently low dimensional that I can essentially like approximate V to very, very high accuracy by whatever method you like, then I can also do this well. Yep.
So in the DP step where we do the minimization, we have to ensure that it is a global.
That's right. Yeah. So that's also potentially non-trivial, which is I was literally going to say that next. So good call. That's a good insight. So yeah, like to be really kind of clear about this, right? The value function, as I kind of recursively go backwards, for LQR, it stays quadratic, which is kind of the magic trick that makes it work. But even for like modest, like benign looking nonlinear problems with a quadratic cost, as soon as the key thing here is, right, when I go backwards, I'm composing V with the dynamics. So even if like my cost functions are nice and quadratic and whatever, if F is nonlinear, when I compose V and F like that, it's going to get gross. And very, very quickly, because I'm doing it recursively backward in time, even if F is only like mildly nonlinear, I have to do this n times. And it gets really, really gross, really, really quick for even like modestly nonlinear stuff. So for LQR, but this thing becomes really bad. Becomes impossible to write down analytically, basically. Even for simple nonlinear problems. And then, as you just pointed out, even if we could calculate it, we'd still have to be able to solve the min over the action value function, right? Which could be non-convex in general, right? And possibly hard on its own. So even that could be intractable. And then, yeah, if you're gonna use some function approximator to like approximate the V in this thing, the cost of doing that blows up sort of combinatorially exponentially in the state dimension. Because you're essentially trying to like, interpolate over very, very high dimensional, vector space or whatever. So that's bad. So why do we care about this then if this is so terrible? So anyone?
I mean, it's nice to find you go up.
That is very nice. Okay, so basically the move now, knowing all that is, you just do this approximately. So if I approximate this dynamic programming stuff with a function approximator for V or S, cool. That's basically RL, right? Like that's what reinforcement learning is. It's just plug in a neural network for V or S. That's what Q-learning is, right? That's like what all these things are doing in various flavors, right? So literally, I would argue like basically all of reinforcement learning is doing approximate dynamic programming with a neural network function approximator for either the value function or the action value function, right? And all kinds of iterations on like variants on that theme. By the way, this is an old idea. This idea has been around for a long, long time, in all kinds of flavors, right? So approximate dynamic programming with a function approximator.
Even within the P single DP set, even if you don't reach global optimum, it's more or less.
Yeah, you do your best, right? And it's approximate. And that is for either V or S, depending on if you're doing model-based or model-free, is very powerful and shows up all over the place. And we're going to do it, right? It's kind of basis for modern RL. Also, another fun fact, which is we've got to wrap up here in a sec. Dynamic programming, also a big deal here, is it generalizes to stochastic problems, where Pontryagin does not. In particular, what you do is you just wrap everything in an expectation. And now all of a sudden, you're solving stochastic problems. That's another big deal. So we just kind of wrap everything in expectations. Pontryagin does not. Okay, so that's it. And then on the way out, I know we're like out of time. I'll just pull up the code for this stuff real quick and walk through it, and this will get posted, and we can maybe peek at it next time as well. Feel free to pack up or whatever. This is back to our same thing we've been doing, same sliding brick. I'm going to actually explicitly check the controllability here by writing down that C and looking at the rank, and it's 2, and this is a 2D problem, so that's cool. I'm now going to kind of write out, yeah, same LQR problem we did last time. We're going to solve it as a QP like we did last time, get the trajectory. And then here's the dynamic programming RICOTTI recursion that we just derived written out, where I go backwards and then I roll it out from some initial condition. I'm going to plot all that stuff and just show you that they match exactly, which we already knew, right? Because we've already got RICOTTI a different way. Cool. This is showing the P's, showing you how they converge to steady state infinite horizon values, right? Showing you I got the same costs. Comparing, this is DLQR, right? So this is computing the infinite horizon K, showing it matches. This is DARE, which you saw last time, which computes the infinite horizon cost to go, shows you those match. And then, yeah, just me kind of messing around a little bit, showing you this sort of sub-trajectory idea. So I start it in the middle somewhere and show you that those things match, like the optimal sub-trajectories match. And then the last thing that we got asked a whole bunch, what are the Lagrange multipliers from the QP? This got asked a lot. Yeah. Gradient of the cost to go. So there's a deep connection between trajectory optimization and dynamic programming, and it is that the duals, the Lagrange multipliers associated with the dynamic constraints in the QP or in general trajectory optimization are the gradients of the cost to go, the optimal cost to go, or the value function, which is really cool. And I would think people would use this more, but they don't, unfortunately. Like there's some deep stuff in there that like is very cool. So it's just showing you that works out in a few different ways. And that we got to get out of here. Thank you guys. See you next time.